Off-policy knowledge distillation can train on teacher trajectories a TRL student never produces at inference. You'll train a student via on-policy distillation on its own completions and report held-out accuracy alongside its memory footprint. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. A large teacher model may solve a task well, but it can be costly to serve. A smaller student can respond faster and use less memory. Yet ordinary training can miss the mistakes that student will make in real use. That gap matters when your product must handle many requests with a limited GPU budget. On-policy distillation closes that gap. The student first writes its own completion for a prompt. The teacher then scores the token choices made along that exact path. The student learns from feedback on its real behavior, not only from polished teacher answers it may never reproduce. We will build a small arithmetic experiment with separate training and evaluation prompts. The student will learn from a larger teacher while generating its own answers. Then we will check whether the compact model remains accurate and practical to serve. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. We first need a stable prompt split, so training and evaluation stay honest. This snippet builds a reproducible arithmetic prompt split with Hugging Face Datasets. Distillation needs prompts that the student can generate from, while the answer column stays available for a separate quality check later. Dataset from dict keeps the prompts and answers readable in one small dataset. Then, train test split uses seed equals 7, which means repeated runs reserve the same examples for evaluation. The visible output confirms how many prompts feed training and how many remain untouched. That separation is important because a student that memorizes training prompts can look strong without actually handling new arithmetic questions. The prompts are ready, but a training run also needs clear rules for generation and comparison. This code configures a compact on-policy run with TRL DistillationConfig. A named and seeded configuration keeps experiments comparable when prompts, generation, and optimization can all change the result. Max completion length limits how many training tokens the student may generate after each prompt. A shorter limit reduces work but can cut off a useful answer. Logging steps records every step so you can inspect the learning signal later. Beta equals 0.5 selects standard Jensen-Shannon divergence, which measures disagreement between student and teacher token distributions in a balanced way. Moving beta towards 0 selects forward KL, while moving it toward 1 selects reverse KL. The output exposes the run identity and divergence setting that should travel with the results. The settings define the experiment, so now the models and reserved data must meet inside the trainer. This example connects the student, teacher, and prompt splits through TRL DistillationTrainer. A compatible teacher matters because the trainer compares both models' next token distributions over completions generated by the student. Model names the smaller model that will be updated. Teacher model supplies feedback, but it does not replace the student's own on-policy trajectories. The held-out split is attached now, so evaluation data remains separate from optimization. The printed parameter count makes the intended serving size advantage visible before training begins. Fewer parameters do not guarantee good answers, but they create the opportunity for a smaller memory footprint and cheaper deployment. For more practical lessons on Python, machine learning, and LLM systems, please subscribe. The trainer is assembled, and the next need is to let the student generate, learn, and save its updated weights. This snippet runs on-policy knowledge distillation with TRL trainer.train and saves the resulting student. For each training prompt, the student generates a completion from its current behavior. The teacher then provides distribution feedback on the tokens in that student-generated path. That is the key difference from simply copying a fixed teacher response dataset. Result.metrics captures the aggregate training loss, which gives a high-level signal about how the run ended. Trainer.state.log history preserves step-level records, so you can inspect changes during training or compare experiments fairly. Trainer.saveModel writes the trained student to the configured output directory. The output shows the final aggregate loss and whether the expected tracking records were produced. A lower training loss is useful, but the real question is whether the saved student answers unseen prompts correctly within its serving budget. This code measures held-out answer quality beside the trained model's serving footprint. The TRL trainer's processing class tokenizes unseen prompts, preparing them for the transformers model.generate call. Deterministic decoding keeps repeated evaluations comparable because the model follows the same decoding rule each time. Batch decode separates each newly generated completion from the prompt text. Then, accuracy checks strip predictions against the reserved answers, so formatting noise is less likely to hide a correct result. Get memory footprint reports the current model tensors in memory. The output places held-out exact match accuracy and model memory together, making the quality versus cost trade-off visible instead of treating model quality as the only goal. When a team must serve a large volume of short, predictable requests, this comparison guides a real decision. A larger student may earn better held-out accuracy, but consume more memory per replica. A smaller student may be the better choice if its accuracy clears the product requirement and allows more concurrent requests. Monitor both held-out quality and failures in the kinds of answers users actually need, because exact match is strict and may not capture every useful response. This example shows why on-policy distillation trains the student on its own habits, then evaluates it on data that training never touched. The teacher provides richer feedback than a single target answer, while the smaller student remains the model you actually serve. Try changing beta and compare the held-out accuracy, training records, and memory footprint. You can also test a different completion limit to see whether the student needs more room to finish an answer. What practical LLM training topic would you like to explore next? Share it in the comments and subscribe for more clear Python and AI engineering lessons.